Hi, everybody. We're going to look at the 520 review session sheet first here for anybody that didn't get a chance to come to the session. So it says a computer company makes, I guess I'm not going to read it for you. You can pause and you can look it up in Google Classroom, or you can read it off the screen here. So go ahead and hit pause, and then after you come back, you can watch the rest of this in 1.5. All right, so now they tell us the percentage of defective trips produced each hour has in oven A has a mean, so they give us the individual mean, they give us for each oven, and then they give us the difference. So it turns out on here, I guess I would, when they say here, does there appear to be a difference between oven A and oven B with respect to the mean percentages of defective chips? Well, they're not asking for it, they're saying a difference in the mean percentages. They're not going to say, they're not saying a difference in, no, they're not saying what's the mean difference between the two. They're saying a mean, what is the difference in the means. So for what I'm going to do is I'm going to do a 2-sample t-test for means. So I'm going to go up to a spot here where I can annotate. So that puts us in phantoms. And we get to go through and we get to review some things about the means here, or about a 2-sample test. Okay, so the very first thing in phantoms is we're going to say let mu a, mu underscore a. We're going to say mu a and mu b represent the true mean percentage true mean percentage of defective chips produced each hour by the corresponding, I'll say by oven A and oven B. Okay, so that's what we're gonna do first. Okay, then the next one, pH, the hypothesis. Okay, so it looks like A minus B is 1.1. If I look at down here, I can tell that the mean for A is higher. So in my sample, so what I'm going to do is I'm going to do, they want just to see if it's different. Does there appear to be a difference between, okay, so a difference, so it's going to be two-tailed. So HO is that mu A minus mu B is equal to 0. That means there's no difference between them. And HA is that mu A minus mu B is not 0. I don't have not equal to in my texting. Okay, so it's a two-tailed test because they ask for a difference. They didn't say whether it's bigger or less. Okay, so now PHA. So now we need the assumptions, and we need to make assumptions. We got to clear the assumptions for both cases. So you can do this in 2 lists and 2 separate things, or you can do it in 1. But we got to get this kind of done. So let's see. So for random chips, they said something about chips being assigned random to ovens. Okay, for both ovens. So that checks the random condition for both. Independent. It said hundreds of chips are baked each hour. So the Now what I don't have here, no, independent observations, and the observations are in the hours. So we have to look at each hour. So it's not replacement. We can just say that the hours are likely independent of each other. Okay, so we're really doing a sample of hours here. And then the next part is random, independent, and so is it normal? So we're doing a t-test here, so we have to take a look at these, and what we would do is we would make a dot plot of this, and we'd make a dot plot of this and show that there are, since there's only 9 observations, we're going to have to make sure that there's no skew in either one of the dot plots and there's no outliers. So I'm just going to say here, since n is less than 10 for both samples must be free, must be symmetric and without outliers. And then you'd have to graph them and show. So I'm going to assume that they're there, but on the test, you would graph them with a dot plot and show. And when you do the dot plot, make sure that, or a histogram, you could do a histogram, make sure that you label the axes. You would need 2 histograms here. Okay, so now we have to name our test. So let's see, I'm going to clear everything, clear all drawings. We're going to do a 2-sample t-test for difference of means. Okay, we're going to do that, and we're going to say alpha is going to be 2-tailed with alpha equal to 0.05. That's the name of the test part. Now we actually have to calculate the test statistic. So the what you're going to have to do there, the SE, the standard error for A, is going to be equal to 5.2 divided by the square root of 9, and the SEB is going to be equal to 3.78 divided by the square root of 9. And then, so then the variance, then you have to, the SE of A minus B is going to be equal to both of those, the square root of SEA squared, because we have to get the, we have to add this, since we're going to combine, we're looking at a combined distribution here of the X bar A's and the X bar B's. We have to come up with, we have to add the variances plus SEB, oops, SEB squared. Okay, that would give us that value. Okay, so let's come over here and let's actually do that. So I need 5.2 divided by the square root of 9. Well, that was dumb. Oh, shoot, I forgot. I can't hit that button. Clear. 5.2 divided by 3. And then 3.78 divided by 3. And I'm going to add those two together. So I'm going to take parentheses 5.2 divided by 3 parentheses squared plus parentheses 3.78 divided by 3 squared. And then, so that's adding the variances, and then I have to take the square root of that. I'll just do answer. Keep forgetting I can't hit the backspace button. Delete, 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 delete. Second answer. 2.14. So I'm going to come back over here to my text and say equals 2.1429. Okay, so essentially what we have now, we can't forget what we're doing here. We have set up so that we have a distribution of all X bar A's minus X bar B's possible. And the null hypothesis says that the center of that is going to be 0. And the standard deviation of that is going to be, or the standard error of that's going to be 2.1429. So that's what it's going to be. So now it's our time to figure out what we got. So we have X bar A. I'm going to do this here. X bar A minus X bar B is equal to, I got to get those numbers, 33.56 minus 32.44 equals, I got to go over here, 33.56 minus 32.44 is 1.12. Okay, so this thing, grab that, is 1.12. So now I have to fit this in this t distribution. So I got to make a t distribution here. I got to turn this into a t-score so I can fit it in the distribution. Right now, we can see that we're inside of one standard deviation. So I don't think we're going to be able to detect a difference here. So our value is within one standard deviation. So now I'm going to get rid of this side over here. Got to remember this is 2.1429. Okay. So I'm going to say X bar A minus B is equal to 1.12, and SE of A minus B is equal to SE of the X bar A minus B is equal to 2.1429. Okay, and the mu of X of A minus B is equal to 0. Okay, so according to our null hypothesis. So now the T is equal to 1.12 minus 0 divided by 2.1429, which is equal to, so I'm just going to come over here. I'm going to hit divided by 2.1429, 0.52. So I have a t-score of 0.52. .5227. Okay, so now I got that's the test statistic. I've got it out. Now I got to fit it in the probability. So PHANTO, obtain a p-value. So the probability of finding an X bar A minus B is equal to, that is greater than 0.5227 is equal to the probability of finding a T that is greater than a T with DF equal to, we take the lesser of the two, so they're both 8 degrees of freedom, so we go down to 8. So remember, that's a conservative version. Take the lesser of the 2 degrees of freedom, and we say is greater than, no, shoot, this is the 0.5227. Back here, this should be the X bar was 1.12. There, sorry, you guys probably saw that mistake. All right, so now, because we're doing a two-tailed test, we're going to have to double this probability to get the true p-value. So the p-value is equal to 2 times. Now I should come up here, and now I have to go to my table. So I'm going to go to my distribution, not my table, so second distribution. And I'm going to go to the TCDF, which is 6. And I want the lower bound to be, since I'm on the greater side, I want the lower bound to be 0.52. And I want the upper bound to be 10 to the 99. 10 to the 99. And then the degrees of freedom is going to be 8 degrees of freedom. And go down to paste and hit enter. You get 0.30875. So now let's get back in here. 0.30875. So if I double that, so now 2 times 0.30875 is equal to like 0.616, maybe even 0.617. So this is really a big p-value. Now we make a decision. Since the p-value equals 0.616, which is greater than the alpha equal to 0.05, we fail to reject the null hypothesis, HO. Right? So now we have to put it in context. There is insufficient statistical evidence to conclude that there is a difference in mean defective, let's see, right here. Does there appear to be a difference between oven A and oven B with respect to the mean percentages of defective chips produced? Right, and then give, so we did that. Okay, so that's the first one. Let's see how we did. Now, you're going to see here that the solution, a complete response, selects an appropriate statistical test. So one way you could do is you could say paired t-test, which we just chose not to do, or we could do a 2-sample t-test. That's what we did. And then we didn't do anything other than that. States and addresses for the necessary t-test. So the dot plot, so showed a dot plot. And then did the correct thing here. Mu A or mu D is equal to 0. Mu A is not equal to 0. So we use always differences. So I like doing that. Mu A minus mu B is equal to 0. That's equivalent to this statement right here. And this equivalent to this statement. So we get a t value. This is for the 2-sample t-test was t equals the one that we just did was 0.519. P-value is 0.61. So we were in good shape there. Don't worry about the sign test stuff. Correctly approximates the p-value. We're done with that. We got all that thing. We didn't do a confidence interval. Correctly states the conclusion. The difference in the mean percentages, samples, chips, isn't statistically significant. There was no difference in percentages. So there we go. So that's how we had to do it. So I think we did it fine. All right. So let's look at the next one. Trains carry bauxite ore from a mine in Canada to an aluminum processing plant in northern state. So again, if you want to pause the video for a second here and kind of get your bearings on this problem, I'll read through it quickly. Filling equipment used to load ore on hopper cars when functioning properly. The actual rates of ore are filling equipment are approximately normally distributed with a mean of 70 tons and a standard deviation of 0.9 tons. Okay. If the mean is greater than 70 tons, the loading mechanism is overfilling. All right. So let's see on this one. So what was kind of important there? Use this. When it's functioning properly, it is approximately normally distributed with a mean of 70 and standard deviation of 0.9. If the mean is greater than 70 tons, it's overfilling. Okay, if the filling equipment is functioning properly, what's the probability that a weight of ore that in a randomly selected car, so a single randomly selected car, so that means that we can use this distribution right here, will be 70.7 tons or more. Show your work. Okay, so this is a probability problem, so or a normal probability problem. So I'm going to start with that. I'm going to say the probability that the weight EIGHT of ore is greater than or equal to 70.7 tons is the same as the probability that a z-score is greater or equal to, and then I do the z-score calculation. So 70.7 minus 70 divided by the standard deviation is 0.9. And that's going to be equal to, so now I'm going to come over here to my calculator and do that calculation. Distribution, normal CDF. The lower, since we're doing an upper greater than version, so our lower version is 70. Clear. Parentheses 70.7 minus 70 parentheses divided by 0.9, and the upper is 10 to the 99th. And that's a z-score, so I turn that into a z-score there. It'd probably be a good idea to put the z-score there, but so now I'm going to go down and I'm going to paste, hit enter, so 0.2183. Now, I'll show you the accompanying drawing that I think you should make here to support your answer, 0.2183. All right, I think as soon as, if you're gonna do a normal crop, remember we said if we're gonna do a normal probability problem, we have to show that we're using the normal distribution. So I'm gonna grab the draw. So I would expect you to have this picture, a nice normal curve, drawn better than what I can do, with the center marked at 70. And then at 1 standard deviation, we need 70.9. So that gets it in there. Now, how do I know the standard deviation? Right at this inflection point is 1 standard deviation, remember? And then right here, this is going to be 69.1. And then now we put ours on here. Maybe even I'm going to use a different color. And then we want to know 70.7. So we're inside of 1 standard deviation. And then we shade that in, and we would put 70.7 there. I don't have enough room in my drawing, but you would put it down where that 70.9 is, right there. Not negative, I'm just trying to draw an arrow. Okay, and then this area right here, once we find it, that area is going to be 0.2183. There we go. So that would be a complete solution for that one. All right, let's erase what I have here. Clear all drawings. Let's look at number 2. Suppose that the weight of an ore of a randomly selected car is 70.7 tons. Would that fact make you suspect that it's overloading? Justify your answer. Okay, you'd say no. Since 28 or 21.8% of cars would be loaded to a weight of 70.7 tons or more, when, this is important, when the equipment is functioning properly, we do not have reason to suspect that the equipment is overfilling. So a couple things that were important in that thing, we have to say, we have to compare 21% of cars be loaded. So 21% of the cars would be loaded there, 70.7 or more, when the equipment is functioning properly. That's important to put in there, that when the equipment is functioning properly. So we do not have reason to suspect that the equipment is overfilling. All right, so let's get rid of that. And then if the equipment is functioning properly, what's the probability that a randomly selected sample of 10 cars will have a mean ore weight of 70.7? So now we're talking a sample of 10 cars. So now we have to come up with the sampling distribution and see the sampling distribution of this mean right here. Okay, so to me, what you're going to do now is you're going to identify that this is going to be a sampling distribution. The sampling distribution of the mean of 10 cars, 10 randomly selected cars, will be approximately normal, since the population is approximately, the population of weights is approximately normal, and have a mean of 70 tons, have a center, I'll say, yeah, have a mean of 70 tons with a standard deviation of, now we're going to do 10 cars, so that's going to be 0.9 divided by the square root of 10. Okay, so that's the standard deviation of the sampling distribution of means. And we can call it standard deviation here because we knew the population standard deviation. Okay, so I'm going to say equals, I don't know what that is, so I'm going to go get it. So 0.9 divided by the square root of 10, enter. 0.28, so I'm going to come back over here. 0.2846, there. All right, so now we got to get the probability. So now what I would do is, I'm not going to do it right now, but I would draw this sampling distribution, and I would put 70.7 in there, and I would shade to the side. So to get the calculation, we can come over here, and I'm going to show you how to do the we'd have to show the z calculation and everything, but I guess I should do that. If I'm saying that you should, I should do it. All right. So what we're going to do is the z is equal to 70.7 minus 70, but this time divided by 0.2846 is equal to, come over here, so 0.7 divided by clear 0.7 divided by 0.2846 is 2.45. So now this is much more, you can kind of think about this. This is much more strange to get a mean of 70 cars that would be at 70.7. We would expect in 10 cars, some of the cars would be below, some of the cars would be above, and we would expect the mean of 10 cars to be about 70. 70.7 is quite a ways off on 10 cars. It means more of them were on the upper side. So this is 2.4596. So now the probability that the X bar is greater than or equal to 70.7 is equal to the probability that we'd find a z-score in the normal distribution that's greater than or equal to 2.4596, which is equal to, and now I'll go over here and I'll do my distribution. So the lower is going to be 2.45. I'm going to do it a little bit differently. I'm going to do it a couple different ways. I'm going to clear that. I'm going to say the lower is 70.7. Enter. The mean, or the upper is 10/99. The mean is 70, and the standard deviation is 0.2846. I'm going to paste it, and I'm going to get 0.00695. Now I'm going to do the same thing again, but this time I'm going to put the z-score in instead of the actual weight. So the lower is going to be 2.4596. The upper is 10/99. The mean of the z-scores is always 0, and the standard deviation of z-scores is always 1. I'm going to paste it. We're going to get exactly the same value. So you can do it either way. I'm going to come over here. And we're going to call this 0.00695 right there. So there's that one. Now C, based on your answer in part C of random sample of 10 cars, or would you suspect? I still wouldn't, okay? So it's not past that 5% level. It is closer. I am more suspicious, but since Oh no, I am, because it's not 0.06, it's 0.006. When the equipment is functioning correctly or properly, I think they say, there is only a 0.6% chance, only 0.6% of 10 car samples would have a mean weight greater than or equal to 70.7 tons. This is cause for concluding that the machine is overfilling. I should probably say 10 car random samples. All right, there we go. And then we could check all of our stuff here if we went through, but I think we're in pretty good shape. All right, that's a long enough video. I might pick up another one. I'll do another one if we need to, but that's a pretty long video. It's gonna take me all night to upload that thing anyway.